So these integrals, these antiderivatives that we've been finding so far, are what are called indefinite integrals, right? An indefinite integral is a function, right? We're taking a function and we're finding the antiderivative of it, and that antiderivative is itself a function. It's got x's in it. Okay. There is something else. There's something called a definite integral. Definite integrals are numbers rather than functions, and we will be talking about those, but there's still a couple of lectures off. All right. So for now, the tools that we have for finding these antiderivatives are pretty limited. Right? It's mostly looking at it and saying, okay, I know a function whose derivative is this. And I hate to be the one to tell you this, but that's kind of how integration works. There are some methods that we have. There are some tools, some formulas, procedures that we can use to find antiderivatives of functions. We're not going to focus a lot on that. There really is a main topic of second semester calculus, but I do want to look at least one. All right, I do want to look at this one that's called integration by substitution. Okay, and here's how it works. What I want you to notice, what I want to stand out here, is if you look at this part here, this 1 plus x squared, and I want you to think for a second, what is the derivative of 1 plus x squared? Right, the derivative of 1 plus x squared is 2x, and you notice how we have a 2x here. That's the kind of thing you're looking for. If you can identify a situation where one part of the integral is the derivative of another part of the integral, that's where you're going to think maybe I can use this integration by substitution method. Okay, so here's how this works. Let me clean up a little bit. All right, what I'm going to do is I'm going to introduce a new variable. All right, I'm going to say let u equal this part that I know how to find the derivative of. And then I'm going to do that. Right? I'm going to differentiate this with respect to x. Du dx equals 2x. You notice, yeah, we haven't used this notation a whole lot, but we really need it here because watch, here's what I'm going to do. I'm going to treat this really like it was a fraction. Right? I'm going to multiply both sides by dx. And I get du equals 2x dx. And now I'm going to divide by 2x. So dx equals du over 2x. Okay, here comes the substitution part. I'm going to replace the 1 plus x squared with u. I'm going to replace the dx with du over 2x. Let's see what happens. Right, this becomes the integral of 2x times the square root of u times du over 2x. Now, look, here's the cool part. The 2x and the 2x, they cancel. All that's left is the integral of u to the 1/2. I'm going to go ahead and make that a fractional exponent. Du. And this I know how to do. Right? This I can do. I'm going to apply my power rule for integrals. I'm going to increase the exponent by 1. So 1/2 plus 1. And I'm going to divide by the new exponent plus a constant. So this is u to the 3/2 over 3/2 plus a constant. And then I can clean up that fraction a little bit, and I'm just barely out of room. So let me jump up here. This is 2/3 u to the 2/3 plus c. Now, it looks like we found the antiderivative, and we kind of have, but we're not done. The original question had x's. My answer needs to have x's. Right? So all I'm going to do is I'm going to substitute back. I'm going to replace the u with 1 plus x squared. And I get 2/3 1 plus x squared to the 2/3 plus c. And that's it. Now I'm done. Right? There's my antiderivative. Okay. Let's try another one. Right, let's try another one. What can I do here? Well, look, this is maybe not immediately obvious, but look, here's what I'm going to try. Let's let u equal 2 theta. All right, if I do that, then du d theta equals 2. Okay, I don't have a 2 in my original integral. But here's the thing. If you're off by a constant, by a constant multiple, like a 2, that's okay. It's going to work out in the end. So you don't necessarily have to have an exact match for the derivative. You just have to have a match, give or take a constant that you're multiplying by. Because watch, now I'm going to solve for d theta. D theta equals du over 2. And now let's do our substitution. This is the integral cosine of u times du over 2. And I can bring that over 2, the 1/2, I can bring it out in front. This is 1/2 the integral of the cosine of u du. And that I know what it is. This is 1/2 the sine of u plus a constant. And now our final step on these things is always to go back to the original variable. Replace that u with 2 theta. And I get 1/2 sine 2 theta plus c. And that does it. All right, that does it. There's my answer. Okay. So how about this one? Yeah, take a look at this thing. See if you can work this one out. Then we'll come back and do it together. Okay, so I'm looking at this t to the 4th plus 1 part. I'm saying the derivative of that is 4t to the 3rd. And it's like I said, it's the t to the 3rds that I care about. That 4 out in front, yeah, okay, there's no 4 in the original integral. I'm okay with that. It's going to work out in the end. So let's let u equal t to the 4th plus 1. So du dt is 4t to the 3rd, which means dt is du over 4t to the 3rd. Excellent. Let's substitute. This is the integral t to the 3rd times u to the 3rd times du over 4t cubed. Now, the t to the 3rds, the t cubes cancel, and I can take that extra 1/4, just bring it out in front. This is 1/4 the integral u to the 3rd du, and this I can do, right? It's my power rule again. This is u to the 4th over 4 plus a constant. And let's say I'm going to do two things at once. Put the t to the 4th plus 1 back in here. This is t to the 4th plus 1 to the 4th over 16, 4 times 4, plus a constant. And that's it. Right? That's it. There we go. And you can check these. Right? You can check these. If you take that function there and differentiate it, you should get back to the original. Right? You'll get back to that original t to the t to the 3rd times t to the 4th plus 1 cubed. Okay, so what's next? You remember when we started talking about derivatives? They had a geometric interpretation. They were the slope of the tangent line, or kind of equivalently, the rate of change of the function. Well, integrals have a similar geometric interpretation. Integrals are going to let us calculate the area under a curve between two x values. All right, so what we're going to do in the next several lectures, we're going to have to do a little bit of a setup. Right? We're going to have to take a couple of lectures and talk about it. It may seem a little extraneous at first, but we're going to have to talk about a couple of additional topics that are going to lead us into the methods for, again, using integrals to calculate areas.